Recording in progress. Okay. All right, guys. Well, okay, everyone. Welcome back to another beautiful day of physics. Let's go through a quick recap of what we learned last week, guys. Basically, last week we learned about the labeling of each and every one part of this transverse wave. All right, we learned about there's two waves, one being a transverse wave, one being a longitudinal wave. A transverse wave, the key important parts are definitely the crest, which is the top part of the wave, the trough, which is the bottom part of the wave, the amplitude that is responsible for the loudness of the sound, good. And then we also talked about the wavelength, where it is just a repeat from where it started to where it ends, where it starts to where it ends here. All right, all these are considered to be one wavelength. If amplitude is responsible for the loudness of the sound, what is frequency responsible for again? Remember how I told you men are lazy creatures? Pitch, very good, Raj. It is the pitch of the sound, guys. The higher the frequency, the greater the pitch. The lower the frequency, the less the pitch it is, right? So this is the things that you need to associate the information with. Then after that, we also learned about the formula for wave, right? Wave speed is equals to V equals to F lambda, right? V, which is the velocity of the wave, is equals to the frequency multiplied by the wavelength of the wave. Depending on the frequency and the wavelength, the speed of the wave can be fast or it can be slow, right? And then we did a lot of calculations last week, then we ended today. Okay. Now, today I'm going to teach you guys how to define a transverse wave and a longitudinal wave. Now, up until this point, I think everyone should know this by now, but essentially there are two types of wave, either a transverse wave or there are going to be longitudinal waves here, right? They are either transverse wave or longitudinal wave. Now, in your exam, if your IGCSEs ever ask you guys to, oh my God, this thing was blocking your view the whole time. Yeah. Okay, guys, anyways, in your exam, right, if they ever ask you to define a longitudinal wave or a transverse wave, you must be able to explain them in terms of their vibration and also the propagation of the wave. Now, what is vibration and what is propagation? Let's imagine, guys, today, this wave here, guys, this wave here is a transverse wave. And this transverse wave could be made out of water. Let's say this is a water wave. And in this water wave, let's just focus on one specific water particle here. Okay, let's assume that there is this transverse wave is a water wave, and we are focusing on this one particular water particle here. Okay, now without the propagation, if we only talk about the vibration of the wave, a transverse wave has vibration that goes up and down. Okay, it has a vibration that goes up and down, meaning to say, right, if I only focus on this particle here, without any propagation, the wave will go up, down, 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 and so on, right? This is only when it has vibration. So how does propagation play in this role here, guys? By definition of propagation is just a fancy term to say that it is the direction of wave travel. Okay, direction of wave travel here. In your exam, if you cannot remember the word propagation, you could state that it is the direction the wave is traveling in, right? So right now, with the direction of the wave traveling in one specific direction, and in this particular wave, the propagation is towards the right. You know, just now how I mentioned that without propagation, the particle will go like this, up, down, up, down, up, down, up, down, up, down, right? With propagation, this wave is going to go up, down, up, down, up, down, up, down, and so on. You didn't see it, did you? Pay attention, don't copy first. That's why I say don't copy first, listen first, okay? Vibration is up, down, up, down, up, down, up, down, up, down, like this, right? With the propagation, the wave will still go up, down, down, but it will be propagated towards the right. So it's being like pushed towards the right direction. Can you imagine this? Without vibration, sorry, without propagation, the wave will just go up, down, up, down, up, down, up, down. With propagation, it will be up, down, up, down, up, down, up, down towards the right. That's why the propagation is the direction of wave travel. Is
It will only towards the right.
yeah, if the wave is traveling towards the right, it could travel towards the left as well, but that's a different example. But the concept is the same. Just you have to understand that propagation is the reason why the wave will travel towards specific directions. And because we understand that vibration and propagation plays into the wave, right? We must understand that if we are asked to define it, guys, if we are asked to define it, a transverse wave have vibration perpendicular to its propagation. This is how we define it. Don't write it down, it will be in the next, it will be in the notes, but just understand first, for definition of a transverse wave, the vibration will be perpendicular to the propagation of the wave. Understand, everyone? Okay, what about a longitudinal wave? Now, in terms of vibration, guys, longitudinal waves will have vibration that are parallel to its propagation. Being to say, without propagation, today, without propagation, let's focus on this particle again. It will just go left, right, 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 and so on, right? With the propagation, right now, with the propagation of wave, because it's being propagated towards the right, it will go something like left, right, 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 and so on. So it's being propagated all the way towards the right. And because of this, when we are asked to define a longitudinal wave, we can say that the vibration is parallel to the propagation of the wave. Okay, so these are the two differences between transverse and longitudinal. One is perpendicular for vibration and propagation. One is parallel for vibration and propagation. Think about it. They'll ask you this in your IGCSEs, so you have to know this. Okay, guys, anyone's got any questions for this part here before I move on? Okay, if there's no questions, then look back at the definition here. If you see here, there are two types of wave, longitudinal wave and also a transverse wave. This is common sense. Longitudinal wave will have vibration parallel to its propagation. The keyword of vibration parallel to propagation. If you cannot remember the word propagation, you can just say that it's the direction of wave travel. It doesn't really matter. Okay, so you can see here, this, I want you guys to draw this away, guys. I want you guys to draw this and this, then yeah, label every other part because I think you have labeled it before and from the previous one. Okay, then the definition of a transverse wave, guys, look at this transverse wave, have wave with vibration perpendicular to its propagation. Vibration perpendicular to the propagation of the wave. Okay. Now, examples of longitudinal wave, like I mentioned last week, guys, there are only sound waves and ultrasound. Guys, you can even add on this ultrasound, which is an example of a longitudinal wave. Sound waves, this is a very important number as well. Only has audible frequency from 20 Hertz to 20,000 Hertz. This number is very, very, very commonly asked in your IGCSEs, guys. So what is this range all about? If you want to understand this range, right, you can kind of imagine why old people, they always cannot hear you talking. You know, like sometimes when you talk to your grandmother or grandfather or someone who is relatively old, if you talk at a specific way, they always cannot hear. They go like, they cannot hear you already, right? What do you say? What do you say? Something like that, right? The reason why is this is because as we grow older, our audible range, right, starts shrinking smaller and smaller and smaller. That's why old people, if their audible range is shrinking smaller and smaller already, right, they cannot hear as well as young people. Young people, we have a large audible range. Anything that happens, we can hear. But as you grow older and older and older, the range becomes smaller and smaller and smaller. And this is the reason why it's always so difficult for them to hear us talk. Okay, so this is also a very important number, guys. The audible frequency is from 20 to 20,000 hertz. A very, very important number. For sure will be asked in your IGCSEs, either in your paper 2 or your paper 4. So you must know this. Yeah. Right, guys. Any questions from this part here? Can see it. Is it too small? If you can see everything, then please record it. Please copy everything now.
So the maximum is 20,000.
Yes, that's the maximum audible frequency. In fact, on YouTube, there's this video that plays from 10 hertz to 25,000 hertz. After a specific time, you cannot hear the sound anymore. In fact, if you're old, if you're slightly older, right, maybe up until 18,000, you cannot hear already, because our audible frequency range is like shrinking smaller and smaller and smaller. Want to listen to the annoying YouTube video? Let me see if I can find. But it will be different for everyone, so and it will be quite annoying. Am I copy this down first? Let's play an example later on, and then annoy everyone in the center. Wait, one copy.
Wait, the L for the transfer range and stuff.
This is vibration. This is propagation. Why is this like this?
Oh, okay, this is vibration.
Yeah, this is vibration. It goes up, down, and then it's being up propagated towards the right mark. Right. For those who are confused, this is vibration. This is vibration and this is propagation. Right? It's almost the same. Okay. Everyone done copying? Good. Let's play a YouTube video to see the audible frequency sound ranges. the sound might get a bit annoying. So for those who are sensitive, you can get ready your what's it called? The volume adjustment button, because it's gonna get loud. Audible frequency range. Yeah, this one that plays from 20 Hz to 20,000 Hz. Let's see how far you can listen up to. Right, it'll be a 2-minute video. And I actually cannot hear anything from here. Do you hear anything? You do? I don't hear anything at all. It's like my range is smaller than most of you guys, really. I'm sharing the right one. Up until here, I don't hear anything. Do you hear something? You do? Really? Oh, I'm getting old. Now I start to hear something. My audible frequency is somewhere around 100. I think everyone should be able to hear this, right? I think everyone should be able to hear all this up until like the maybe near 20,000 mark. Like here, I cannot hear it. Do you hear something? Do you hear anything from here? I don't hear anything right from here. Like the last few seconds are like from 18,000 here onwards. I can hear up until 16,000. Here, after here, I don't hear anything at all already, because my range is obviously shrinking faster than you guys are. So here it's like zero sound to me. 你听到东西啊? Yeah, so yeah, the audible range is actually going to shrink further and further and further and further and further. For me, I'm somewhere around 100 to 16,000 Hz. I can still hear, and after that, I cannot really. Right, but a normal healthy human ear is anywhere from 20,000 for me, because faster, right? Anything else from there I cannot hear. This is my range. Okay, everyone, good experiment. Yeah, and finally, this last part here, right, is basically talking about examples of wave. Guys, in your IGCSEs, you have to understand that only sound and ultrasound are longitudinal wave in your syllabus. Every other wave, right, is going to be a transverse wave. For example, tsunami waves, which is essentially water waves, right? Light waves, the name suggests itself. And electromagnetic waves, guys. Electromagnetic waves is a whole new chapter of its own. It includes radio wave, microwave, infrared, visible light, ultraviolet, X-ray, and gamma ray. All these are electromagnetic waves, and all of them are transverse waves. So, in conclusion, you just have to remember that sound and ultrasound is longitudinal wave. Everything else is going to be a transverse wave. Okay, everyone? Understand?
Sound and ultraviolet.
No, sound and ultrasound is longitudinal wave. Only these two, right? But of course, sometimes in the question, if they have like stupid spring thing, right? You know, like the one we mentioned last week. You press the spring, then it like kind of goes this way. That is also a form of longitudinal wave. That is also a form of longitudinal wave. But as long as you flip it up and down, right, then it's going to be a transverse wave. So yeah. Just be careful. They always ask this in your paper too. What is an example of a longitudinal wave? They'll give you a lot of random waves. You just need to know that a what's it called, the sound and ultrasound is longitudinal wave. The difference between sound and ultrasound is that sound is anywhere from 20 to 20,000. Ultrasound is beyond 20,000 hertz. This is the main difference only. It's just a difference in the frequency. That's why it's called ultrasound. Ultrasound is used like, like those baby to see the baby inside one, right?
Yeah.
Yeah, that one is ultrasound. So the concept is they'll bounce the sound into the baby bump, right? And then depending on how fast the sound come back and how hard the sound come back, the computer will generate the image from it. That's why babies always use ultrasound, because it's safe. X-ray for a pregnant lady is equals to killing the baby, so no one does that. Ultrasound is safe, but you won't be able to hear it. It's like you just scan on the stomach, see how pregnant you are. Okay, so moving on from there, this is the more important part of this chapter, guys. This is super important, guys. We're going to go through three phenomena that a water wave can go through. They are namely going to be the reflection of the wave, the refraction of the wave, and also the diffraction of the wave. Let me bring you through the first two first. I'm pretty sure everyone knows a reflection of the wave, right? The most common reflection of the wave is when you're in the mirror, right? Essentially, light waves bounce into the mirror, and the mirror bounces back that light wave. That is a form of reflection. Right, that's why we see mirror is equivalent to reflection. For reflection, it is the most easy phenomena. Pay attention, stop looking at your fingers. The reflection is the most easy phenomena, right? What happens is you can imagine these are going to be your water waves, right? For those who do not know why these are water waves, these are basically what we call wave fronts, guys. They are basically what we call wave fronts. And wave fronts are basically just the top viewing angle, top view of a wave, guys. So if I were to draw out the graphical representation, right, let's imagine by the side view of water wave, they kind of look like this, right? The water wave, they kind of look like this, right? So wave fronts are the things that we only see on the top end, right? So if I were to draw a graphical representation of the top view, right, I'll only be able to see the crest of each and every one of these waves. So that's why you will see these things here, right? This is the top view, guys. The meaning is say my eye is like in this position looking down, right? Whenever you see these lines here, they are called wave fronts. Wave fronts is just a top view to see the wave, and they'll only see the peak of the wave, right? That's why if you ever roll a plane across the sea before, sometimes you kind of see like there's like block, I don't know what's it called, lines and lines and lines on the sea, is because you can only see the peak of the wave only. Everything else you won't be able to see. And these are what we call the wave fronts. That's what I'm talking about, right? Hey, everyone understand what I'm talking about, right? Those who are online. Yeah, so these are wave fronts. It's basically just the top view of the wave. Okay. Now for reflection of the wave is very straightforward. Today, if I have a wave coming down onto a barrier, right, what's going to happen is it's obviously going to hit the barrier and it's going to be reflected upwards. Now, for reflection, there are a few rules that definitely apply. Number one, you definitely need to know that this thing here is what we call the incident wave. The incident wave, and this is obviously the reflected wave, right? The incident wave and reflected wave will have an incident angle and also a reflected angle. The angles are dependent on where this thing hits the barrier. Okay, so let's imagine it hits somewhere here. Okay, if it hits somewhere here, it means to say, right, I'm going to actually construct a normal that is perpendicular to the surface that hits here. Okay, this line here is what we call a normal. Something that you're going to see very often, guys. A normal is basically just a reference point line that is perpendicular. Don't draw first, everyone pay attention now. A normal is just a reference line that is perpendicular against the surface where the wave hits. Okay, now why is this normal important? It's because once we have the normal, right, we can say that from the incident wave to the normal, This is what we call the incident angle. From the normal to the reflected wave, this is what we call the reflected angle. And of course, for reflection to occur, the incident angle must be equals to the reflected angle. Very, very important. Now, a lot of students because they don't understand the concept of the normal, right? They'll tell me something dumb, they'll tell me that, oh, this here is going to be the incident angle, and this here is going to be the reflected angle. Okay, which is not correct, guys. Remember, I need to emphasize this because this is going to carry on to the next few chapters as well. The angles are always with reference to the normal, meaning to say this is the normal, right? This is the wave, right? This is the reference point. This is the incident angle. This is the normal, right? This is the reflected wave, right? This is the reflected angle. The angles are always with reference to the normal. It won't be with reference to this line here. This is no. Very, very important now, guys. A lot of students always make this mistake, which I will then physically abuse them until they remember, right? So for those who are online, of course, you get to escape. But always remember, incident angle is with reference to the normal, and reflected angle is with reference to the normal as well. Not the base. So very important. Shit. Very important. Okay, so this is not it. This is okay. So from here, the statement is very straightforward, right? Reflection occurs when the incident wave is met against a barrier. This is the incident wave, this is the barrier. The reflected wave bounces off with the same angle as the incident wave. This is the incident angle, this is the reflected angle. There are a few things that remain unchanged and a few things that change. First and foremost, the frequency does not change. Meaning to say, if this wave came in at 100 Hertz, it will bounce off at 100 Hertz, okay? Now, the speed does not change as well, meaning to say, as it comes in at 10 meters per second, it will still be 10 meters per second, and the wavelength will definitely not change as well. This is also because of the V equals to F lambda formula, right? Frequency didn't change, speed didn't change, frequency and speed did not change, then obviously your wavelength is not supposed to change. I mean, you say however long this is, it will be however long this is. Okay. Now, very important, everyone pay attention to this next statement, guys. It doesn't matter if it's reflection, refraction, or diffraction. Frequency will never ever change. Okay, in your IGs, right, they love to ask you this question. They ask you, okay, this wave is going through reflection. State what happens to the frequency. The answer is there is no change. Or they'll ask you something like, okay, this wave is going through refraction. State what happens to the frequency after the refraction. The answer is there will be no change. Or they'll ask you, okay, this wave is going through diffraction. State what happens to the frequency after diffraction. It will be the same damn answer as well. The frequency will never ever change, okay? Very, very important. This one for sure will be asked in IGCSEs. You need to remember that frequency never changes regardless of whatever phenomena it is. Very, 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 very important. Frequency never ever changes. And that's why you see later on, you see here, frequency doesn't change. This is for that refraction. You see here, frequency doesn't change again, right? This is for diffraction, guys. Always remember that frequency will never ever change. Okay? Are you in the right page, by the way? Oh, you are. This is okay, so guys, anyone with any questions for this part here? Okay, if there's no questions, then guys, you'll notice that I said these things don't change, right? Frequency, speed, and wavelength don't change. Well, of course, there are things that definitely change. First thing is direction, and the second is velocity. Now, if I said that just now the speed did not change, and I said that it was 10 meters per second and 10 meters per second here, how come when the direction changes, the velocity changes as well? Why? Can anyone tell me why the velocity will change when the direction changes? Very good, Raj. That is the exact answer. Guys, speed is actually a scalar quantity, whereas velocity is a vector quantity. Today, scalar quantities only have magnitude. That's why the magnitude here does not change, right? But since velocity is a vector quantity and it has direction, as soon as the direction here changes, guys, as soon as the direction changes, the velocity is said to change as well, even though the magnitude did not change. Very important, I guess. This is a concept. It's a concept that you must understand. Okay. Yeah. Everyone done copying this one? Okay. Yeah, I think shouldn't be a problem for reflection of the wave. Very easy, straightforward. Next thing we're going to do is refraction of the wave. Right. Now, if you talk about refraction of a wave, guys, I think everyone has definitely experienced refraction before, right? Like, for example, if you drink from a cup of, sorry, from a bottle, from a cup here, and let's say the water is up to this level, and this is your straw from the top, right? You'll always notice that your straw is kind of bended like this already, right? In the water. Have you guys experienced this before? Know what I'm talking about, right? Right, the bending of the straw. Basically, this is due to refraction, guys. This is due to refraction. By definition, guys, refraction occurs because there is a change in speed of light, guys. Because there is a change in speed of light, we see it differently. For example, if let's say, right, I have my eyes from here, right? The way that I see this thing here will obviously be the speed of light, right? Which is 3 times 10 to the power of 8 meters per second. But the way I see this, because water slows down the speed of light, right? So when it comes back to my eye, probably it will be somewhere around like, I don't know, maybe 2 times 8 to the power, 2 times 10 to the power of 8 meters per second. And because there is a difference in the speed of light, there will be a difference in the way we see things. That's why when we look into the swimming pool, you know, like, have you ever stood on top of a swimming pool and then you look down the swimming pool and you see that, oh, it's quite shallow. Then when you jump in, you're like, oh shit, it's quite deep, right? Why this occurs is because there is a change in speed of light, which is also refraction, guys. So from here, if you know what refraction is, in your syllabus, they'll ask you something like this, okay? You need to understand that when water waves travel from deep region to shallow region, because there is a change in speed of the wave, there will be refraction occurring. And in order to really understand refraction, I want you guys to remember this story. This is story time yet again, guys. If you guys ever been to a beach before, right? The surfing beach, to be particular. Have you ever noticed that from super far away, the waves are like super tall, right? And then as it comes closer to the shore, you'll notice that the wave starts coming down. And then when it comes to the beach, right, it kind of just, the water kind of just like washes your leg and then it'll go back down. Why do you think there is a difference in the magnitude of the wave? What do you think is happening in terms of the speed? In terms of the speed, what do you think is happening when it is super far, the wave is super far away, and when it's very close to the shore? Good. The speed actually decreases. Very, very good. So from here, first things first is I understand that here the velocities are much higher and here the velocities are much lower. That's why when it's super far away, the wave is like super tall, right? Then it comes closer, it kind of just washes against your legs only, right? Now from here, if I understand that here the speed is faster and here the speed is slower, right? The next thing I need to associate is that this here is a deep region, right? This here is a deep region, right? The next thing you need to associate is that the deeper the pool or sea or beach or whatever, the faster the wave is going to travel. Whereas this is very shallow, right? This part here is very shallow, right? The shallower it is, the slower the speed of the wave. Okay, so this is the first story I remember. You're on a beach, you're on a surfing beach, super far away, the waves are super tall because it is very fast. When it comes to the shore, right? When it comes to the shore, the waves are just like washing against your legs because the speed is much slower already. Very, very important concept. You must know this. Okay. Okay, I can associate, think about it in your head and associate that deep region, the speed is faster, shallow region, the speed is slower. Okay. If you can understand that, right, looking at refraction for water waves will be much more logical. Refraction occurs when a wave is traveling from a shallow region to a deep region or vice versa. It could go from deep to shallow, it could go from shallow into deep. Okay. Now, when the speed decreases, guys, let's look at the first example first, guys. Look at the first example here. Now, I know for a fact that in the deep region, the velocity is much higher. In the shallow region, the velocity is much lower. Now, according to my V equals to F lambda formula, guys, just like I mentioned, what happens to the frequency? The frequency will be the same. It will stay the same, right? So can I straight away associate that if I have an increase in velocity, I will have an increase in wavelength. If I have a decrease in velocity, I will have a decrease in wavelength, right? Because the frequency is the same, right? So from here, then after that, I need to understand that, as it goes from deep into shallow, because here the speed is faster, what's going to happen is the wavelength is going to be further. But when it goes from deep into shallow, because the speed is slower, you'll notice that the wavelength decreases with accordance to the formula because frequency stays the same. A decrease in velocity will cause the speed of the wave and the wavelength to decrease as well. Understand? Okay, this is the first concept you need to understand. It is according to the formula, guys, because frequency is the same, the decrease in velocity will decrease the wavelength. Now, if you can understand the wave decreasing and increasing because of that, right? The next part is the more realistic one. This part here is actually what your IGCSEs like to ask you guys. Okay, so how will they structure the question? They'll say something like this. Okay. Let me try to draw it as nice as possible. So we have a square here. Then we have a square. Okay. Okay. After that, let's just then right now we draw the wavefronts. So let's start off easy first. I'll say that this is deep and this is the shallow region. And this will be the shallow region. This is the deep region. Okay. Let's imagine right now we are looking from the top view, guys. The side view of this will look something like this, guys. The side view will look something like this here, okay? This will be the deep region and this will be the shallow region, and we're looking from this point of view. Okay, this thing here right now is just like this thing here, but slanted a little bit, right? We purposely slant it so that there is a line here, right? This is the deep region, which is this part here. This is the shallow region, which is this part here, but we slant it a little bit. This is how the structure will be. From here, first thing first is if you're asked in your IGCSEs, they'll say something like complete the water waves after they go through diffraction. Now, when I see, refraction. When I see this scenario here, right, first thing I think about is that it goes from deep into shallow region. If it goes from deep into shallow region, what's the speed in a deep region again? High or low? High, right? The speed here is going to be low. So I know for a fact that coming from deep into shallow, the speed of the wave is decreasing, right? Decreasing speed, right? Right. So, okay, this is the first thought I have in mind. Now, after I have the first thought in mind, right? Let's say if there was no difference in deep and shallow, by right, the water wave would have looked something like this, right? The water wave, if let's say this was here, right? It will look something like this, right? It should have looked something like this, right? But because right now I know that the speed is decreasing, I can say that the waves after they are refracted will be lagging behind. Lagging behind means the origin is straight, right? If it's lagging behind, it's going to start looking like this long. It's not looking like this, it's not looking like this. And I need you to know that these two lines are definitely in parallel with each other, guys. They are definitely in parallel with each other. And since I have these two lines as reference, right, then I can start drawing the rest of it. I know for a fact that once the wave goes through this region here, it will be refracted and it will move upwards instead because the wave is lagging behind already. Okay. What about if you go from shallow into deep? If it goes from shallow into deep, let's say the same example here. Shallow. Right. I know for a fact that the velocity here is lower, the velocity here is higher, right? This is to say coming here to here, the speed is actually increasing. If the speed is increasing, yet again, by normal, the reference by right, the wave should have been straight line like this, right? If just now, because the speed is slowing down, it lags behind. Right now, because the speed of the wave is increasing, it will actually lead forward, guys. It will lead forward, and lead forward. Right? Meaning to say, if they ask you to draw, you look something like this. The wave would have been something like this, to go down like this here instead. Okay? The wave will either be lagging behind or it is going to lead forward. And you do not need to purposely readjust the wavelength. You'll notice that as soon as it starts lagging behind, the wavelength here for sure decreases. As soon as the wave starts leading forward, the wavelength here will automatically increase, which is all in line with the V equals to F lambda formula, guys. So this is the concept that you need to know right now. It's the wave is either going to lag behind because the speed is decreasing, or the wave is going to lead forward because the speed is increasing. Before I move on, anyone's got any question with this part? This part is very important nowadays.
So, decrease and lag.
You'll lag behind. By right, it's supposed to be a straight line, right? If it lags behind, then it tilts backwards. It will be at the back of the original line. If it is increasing speed, then the wave will be at the front of the original line. Can you see like this part here? This is supposed to be one straight line, right? This is at the back of the original line. This is one straight line here. This is the back of the original line, right? And then if the speed is increasing, this is the original line, right? It will be in front of the wave. This is the original line, right? It will be in front of the wave. So it's either going to lag behind or it's going to lead forward. Okay. Oh yeah, you're going to draw. But everyone understand what I'm talking about? Yeah, I'm going to screenshot this, then I can send it to the group later. But if not, you're going to draw this. Okay. Now from here, if you can understand the concept right now, it will be much more easier to read this. You see that this is the deep region, right? Deep region, the speed is fast, Shallow region, the speed is low, right? By right, it should be an original line like this, right? It should be straight line, because it's starting to slow down, so it lags behind. Then once it lags behind, you can draw the rest of the consecutive ones already. Right. Same thing for this one as well. This is the deep region. This is the fast one. This is the slow one. By right, the line should be straight like this, right? It's all lagging behind. If I only have one small shallow region here, only this part will start lagging behind. And then when it reaches here, the speed will have been different already, right? And it will all look like this. Okay. Up here already now.
So it creates more of this, and it creates more of this.
Oh,
Oh, wait, is on this. Can you show up in the graph?
oh, sure.
This big one from this.
Why?
This is like big to show.
Oh, because one is tilting like this and one is tilting like this instead. Can you see? This one is tilting like this. This one is tilting like this. And because of that, there's going to be a difference. So there is no specific format. You actually need to know what is going on, then only you can start doing the questions. Hmm? 帮忙吹。 哦，它是什么？Oh, the last one here. The last one here is just a FYI example only. You don't really need to know this. You know, like how the wave is supposed to be like it's supposed to be like straight. Wait. What? You know how the waves are supposed to be like straight, right? When it reaches this region here, because this part slows down and it continues the fast speed here. This region is fast speed, slow speed. After that, this one continues slowing down again. This one still moves at the normal speed. This one slows down again. Then eventually, when it comes back to the normal region, it's like your friend is running in front of you at the same speed as you already right now. So you can see that there is going to be a difference in the wave coming up and down. Okay, this one you just ignore it. It's not important. But the concept is just that this part slows down the wave, slow down the wave, slow down the wave, slow down the wave. That's why eventually they will all slow down in the middle. Okay, but it's FYI, they don't really ask this in exam. They'll ask this and this though. This and this very commonly asked in your exam. Very, very commonly asked. Okay. And for refraction, only frequency doesn't change. Everything else changes. The direction, the speed, and definitely the wavelength. The direction, as you can see here, the speed, as you can see here, and obviously the wavelength. Okay. Okay. Guys, I'm not going to go through this part here. It's a bit long. But can you copy this down first, guys? Let's use the remainder 5 minutes to copy everything down from here. And I'll explain the concept to you guys next week, guys, because this is going to be a long one. Just copy this down first.
All the graphs.
Yeah, all the graphs. Oh, by the way, guys, I want to highlight that this one here, you draw the wave a bit further back, because by right, the wavelength should be larger than this gap here. Okay, this one, just draw the wave a little bit further back. Don't draw like so close together. Draw them a bit more separated apart. Okay, draw them a bit more separated apart. Yeah, just draw this now for the rest of the 5 minutes. Then we'll end class. You're supposed to draw the Wi-Fi thing more nicely, yeah. And yeah, just draw it nicely, yeah. Hello, my name is Elon Musk. Hello, my name is. Yes, 你全部人都去 sports event。有一个 sports day 在学校 ，so 他们全部都没有来。
不是 sports day 是在
不知道。
不知道。是不是所有华小？
华小。Okay, copy everything down. Hurry up. Then we'll continue this next week. Then we'll be doing exercises really next week. But it's acceptable. Yeah. Draw the third and the fourth one as well.
what's the difference between third one?
Oh, the wave is much smaller on the fourth one, and that's why it doesn't bend as much. The third one bends more, that's why you can see it becomes more circular.
Oh.
Yeah, copy the sentence down, and you are done for the day. Why the name? Okay. Okay, everyone, done copying. I'm sorry that the time is it for it today already. Some of the students need to go for the maths class. For those who are not done copying, please take a screenshot and draw it. And draw it on your own later. Okay, I need to give up the time for maths class already. All right, guys, we'll continue this next week, guys. We'll continue this next week.